Hi everyone and welcome to today's session. And today we'll be discussing a very interesting paper known as I-JEPA, or Joint Embedding Predictive Architecture for Images. So this is actually based on this vision by Yann LeCun to create autonomous agents. And in this framework, a very important role is this JEPA architecture, which predicts things in latent space. So this idea of prediction in latent space is very powerful. I believe it a lot. And I think you not just need to do it for one latent space, you need to do for many different hierarchies of latent spaces. Yeah, so before we move on to like this kind of further discussion, let us firstly see what this paper is about. Okay. So one of the key insights that Yann LeCun has is like, do you need to predict everything? So this is a picture of a car driving, all right? I mean, some drivers driving on the road. So just a quick question. If you are the car driver here, okay, what would you need to know when you drive on the road? What do you need to see? Okay, do you need to know everything in this picture? Like, do you need to know how like these leaves move? Okay, do you need to know how this like whether this grass is moving or not? Okay, so yeah, not really, right? You don't need to know all this. If you are driving, you don't need to know all this stuff. All you need to know is that like where are the cars? Where are all these cars here? Where are these cars moving? All right. Where are these cars moving? You don't really need to know like how each of the like whether or not there's like birds, unless the birds is coming to hit you. All right. You don't need to know whether the trees move. All right. So these are some stuff that you can see in your daily life. Like if you don't pay attention to a lot of things, you actually don't know them. Okay, because our brains just don't really predict those things that well. Like you won't predict the leaves at the nearby tree. You just know that there's leaves there. Okay, unless you really zoom in and focus your attention there. If not, you wouldn't know about all this stuff. Okay, but for decades, okay, image generation, what image generation has done is that it's trying to predict pixels, exact pixels of the environment. And that's the problem, you see. If you try to predict back the exact pixels of the environment, what happens? Okay, this is a very good analogy again by Yann LeCun. So imagine you have this pencil over here. Okay, this pencil, you drop it down. Okay, it can drop at any direction. It can drop on the left, it can drop on the right, it can drop like 360 degrees, any angle. So if you can drop your pencil at any angle, and you don't know what angle the drop would be, knowing that you lift up your fingertip from the pencil, what would be the prediction of the pencil? So anyone can tell me, like, if we don't know exactly which direction the pencil is dropping, what will be the prediction of the pencil's like next position?
Lying flat.
Yeah, okay, lying flat, yes. But in terms of like, if you are talking about upwards view of the pencil, you will predict the pencil everywhere, right? It's something like, Schrodinger's cat, you don't know, that's why there's a lot of uncertainty. Everything will be a blur. Okay, I'm just going to draw many pencils here. But the idea is that you will predict everything as a blur. And if you were to optimize your loss function in pixel space, what you will do is you will predict a mesh of pencils. Like basically you will predict very blurry pencils here. Like you will predict blurry images if prediction is done in pixel space. Okay, that's for the purpose of generating images, all right? But for most times in our lives, actually, we don't really need to generate back the original input stimuli that we observe, all right? In fact, what we remember in our memories is also a very low dimension of the input stimuli. We don't remember people's faces very well. We don't remember the details of a room very well. Yeah. So this image generation is actually a very difficult problem. All right. What's actually a better problem that self-learning agents can do is to just use the information from the stimuli to do some prediction. So these are more of like the downstream tasks. Like given like this picture that I see about the car, where should I drive? Okay, in order to not collide another car. So that's a decision-making task. So if we want to do a certain task, we have a certain goal we want to do, right? What you need to focus on and pay attention to will be very different. Okay, you look at this diagram here of the car. If I want to drive perfectly on the road, okay, then I'll need to predict the other cars. I need to predict how the cars move. Okay, but if I want to, like, imagine I have a jetpack now, I can fly. Then now I will need to predict how the birds fly, how the tree branches might sway, this kind of things. And you will begin to develop a prediction model for these things that are deemed important. Okay, so this is my view on intelligence. if your action, okay, that you need to do, okay, involves, you only will be able to predict things that are related to your goal in mind. So if your goal is to get from point A to point B, whatever things that can interfere with your getting from point A to point B, you will learn how to develop a predictive model for that. And that predictive model can come either from this neural network training, or it can come from memory. So actually there's two streams of learning, and this is my view right now. So this actually, the idea of not needing to predict everything, that's actually the key idea of JEPA, Joint Embedding Predictive Architecture. Why predict the high dimensional stimuli when you can do the low level? Okay, so this is a very, very crucial point here. Okay, let's move on. Yeah, if any time you want to ask anything, feel free to just go ahead. Okay, so one of the most popular architectures right now is the transformer architecture. And this is predicting back in the same input space as before. Okay, I'm not going to go through the attention mechanism here, but the idea of the transformer is something like that. I am a, then you have to predict the next word, right? And over here at the output probabilities, you get like student 80%, cat is 20%, something like that. Yeah. So one thing about the transformer is that the prediction space that the transformer has is actually the same space as your input. So this is an anomaly for most prediction cases, because most of the time when we do prediction, okay, we actually are not predicting the same input space as your stimuli. You're predicting like in a lower space. Okay, for language, the tokens itself actually, or fortunately, is actually quite discrete. It is less than 100,000 tokens. So you can do like sort of a softmax across less than 100,000 tokens to get your token. So this is a special case. For images, can anyone think? Okay, images, can we predict the whole image as a token? So, and anyone want to think about it? For words, yes, we can split the text into tokens. All right. Can images use the same method as transformers to do it? Any views here? Or I mean, not just
one problem I can think of is something similar. If you want to like assess the quality of an entire sequence of sentence, right? The same problem is also here, which is there are just too many combinations of possibilities.
Yeah. Okay. So that's also my view here. So, in sentences, right, you need to, like, I am a student, this must be a noun. So there's certain structures that you want to fulfill. The images, actually, the structure is not just one direction. The structure is two directions. So if you look at an image like that, if let's say I draw a table. Okay. Apparently I don't draw very well with like my mouse, but let's say this is a table, all right? So imagine if you are predicting like maybe the next pixel, you kind of need to know like where exactly is this, like let's say you already have this part here, then you need to predict exactly this pixel here, and this pixel here, you need to know like up, down, left, right, diagonal. So actually there's a lot of different conditionals here. Like you not just need to condition on the word ahead or the word behind, you need to condition in different spatial geometries like upwards, downwards, leftwards, rightwards. So if you were to just do a transformer architecture, like if you naively just take a transformer and then maybe try to form different like tokens of various parts of the picture, like for example, if we take this part here and then we just split like that, if you form this as one token here and this as another token here and this as a third token and this as the fourth token, if you do something like this, you are going to lose out this like spatial geometries like up, down, left, right, which will not be preserved. It will not be here. It won't be like captured here. It's not that easy like a sentence. All right. So for images, it's kind of hard to do back the same input space mapping. All right. So this is the problem of high dimensional stimuli. Right. It's not as easy as words. You can discretize them. Images, if you think about it, if we talk about the pixel space, we have red, green, blue, and maybe transparency. All right. Each of them in computer right now is 255 dimensions. Okay, of course, we can take away the transparency. Okay, we can just do red, green, blue. So one pixel, can you imagine like how many, actually it's 256 because it's 0 to 255. is 256 times 256 times 256 possibilities. Okay, I mean, you can also times another 256 for transparency if you want to consider that. Possibilities for each pixel. And you know, that alone is more than the amount of tokens you have to predict in the transformer already. Okay, so people have tried for years, okay, for years. It's not just I-JEPA, years. They tried to just take an image, they mask out certain components. Like, for example, they just say, okay, I'm going to try to do some form of self-supervised learning. Okay, I'm trying to just mask off this part here. And then you're supposed to predict what this part is. Okay, for years, people have been trying to do this and it has failed. Okay, then the main reason is because like it's just very hard to generate back the pixel space, because the pixel space is just like too high dimensional, and it tends to be blurry if you put the loss function in the pixel space. So perhaps we can do the prediction in like another space that could be like more amenable for prediction. So that's exactly the like what I-JEPA is trying to do. Okay, so this is some examples of how we can do different predictions using JEPA. So in the JEPA architecture, the first one is where you have your input stimulus. Let's treat X and Y as like images now, okay? Because now we are talking about images, but X and Y can be different things. It can be like sentences, or I mean the tokens in the sentence. It can also be audio. So it can be different domains. Okay, this is not specific to image, but let's just view this whole thing in image for now. So this, we pass through an encoder. This encoder and this encoder can be different. Okay, but typically I would say that both should be the same, because I mean, if you are talking about encoding the same stimuli into latent space, it should be the same encoder, right? I mean, you wouldn't want to encode like my first image with maybe like a CNN A, and then my second image with CNN B. Then, you know, your latent space may not be consistent. So usually the encoders are the same. All right. And then what you need to do is you need to check, okay, whether or not this prediction here, okay, is it the same or not? Okay, so sorry, here there's no prediction at all. Here what we are trying to do is we are just, because there's no predictor, you see? So what we are trying to do here is we are just trying to, you know, okay, so this is basically just using this architecture to form a latent space prediction. And then we want to make sure that the latent space is like sort of the same for both of them. So, okay, so take back what I said, because there's no predictor here. This X and Y encoder are actually different. Okay, so what we want to do here is we want to learn a mapping of X and Y, and such that the distance between this mapping is the same. So this is actually for different modalities. So for example, this is audio. Okay, I got confused here. I was referring to the JEPA I did. So audio, text, or image and text, you know, like your clip embeddings. So you go pass through a certain kind of encoder, and then what you want to do is you want to make sure that the latent space representation is the same. Yeah, so this is more or less the first kind of architecture. So this is great in a lot of use cases. Like clip has been used for many, many things involving text and images. Right, the second kind of architecture here is the generative architecture. And this generative architecture again uses a sort of latent space, I guess. So you look here, you have, oops, why did I draw an arrow? You have an X here. Okay, this passes through an encoder. And then what you want to do is then you want to decode again. Okay. And then what hopefully you get to do is you get to, okay, so maybe this X here can be the mask image. And this Y here is the full image. So if you want to like predict mask images, one way we can do is we can encode in some latent space. You give some information about the patches in this Z variable here. Z is like the latent variable that you can add in. Okay, and then once you have this in the decoder with the representation in the latent space from the encoder, you can try to decode the message back here. Okay, and this decoder here, okay, decodes it back in original input space. So if let's say you are talking about pixels, it'll be back in the pixel space. So stuff like this, some architectures are like the mask autoencoder, where you try to predict back the pictures back into pixel space. Okay, but however, you know what I talked about earlier, if you predict back in the pixel space, you might get a bit of blurry stuff, because you know, if your loss function is a mean square error in the pixel space, if you don't know how the pencil would fall, you will just predict a blurry blob of pencils. Okay, so this part here has been done also, wasn't too successful. So okay, mask autoencoder is not bad, okay, but it's still like it's still lacking something. It's still not like good prediction of the mask parts. All right. So this is
Sorry, can I ask?
yeah.
So I thought actually if the outcome is uncertain, right, then the fact that the prediction is just a blurry blob, actually from my point of view, that's a good thing because it exactly tells you the fact that the outcome is not certain.
I guess so, yes. I mean, if you are talking about prediction wise for downstream tasks, yes. But if you are talking about your task right now is to do some image generation, then you wouldn't want a blurry image. So it depends on your use case.
Okay, I see.
Yeah, so actually image generation is not easy at all. It's not easy. I don't even think humans can do image generation well. Yeah, I mean, like a lot of people are not very good at reproducing photos. Yeah, so this domain of image generation is really a difficult problem. Yeah, so generative architecture, yes, it uses latent space to encode, but the decoding goes back into the original space. It can be very difficult to learn from it. Okay, and now we talk about JEPA, okay, the Joint Embedding Predictive Architecture. So you can see that it's exactly the same as the generative architecture. It goes into this predictor. Okay, it gets some info about the patches over here, the same stuff. Okay, what's the difference? The difference is that we also, okay, if this is the same domain, all right, okay, different domain, you use different encoder, but if let's say Y encoder is also image, all right, and X is also an image, you should typically use the same encoder and decoder because you want to preserve the latent space, all right? So if both encoders are for the same space, what we do is we convert X into a representation, convert Y into a representation, and then what we want to do is we want to use some hidden variable Z as some additional info in order to use this latent space to predict the other latent space. Okay, so you might be asking me why go through all this trouble, right? Why do you want to go into latent space to predict? Why predict in latent space? This is a big question, right? Why predict in latent space? Any suggestions? Why do you want to do the prediction directly in latent space?
You already mentioned it just now, right? So for different tasks, you just care only a very specific subset of the information from the image. So if you can find a correct subset of information you need, then it's much efficient. And I guess this latent space is exactly that thing you want.
Yes, correct. So a lot of domains, right, it can be represented in a very easy part in like a latent space. So let me give you an example here. So suppose I have a sine wave. Okay, this is very, very confusing in the time domain. Okay, but if you go into the frequency domain, if let's say your latent space is the frequency domain, it's just going to be like a certain block in the frequency spectrum. It's the frequency and this is the power or magnitude spectrum. Yeah, so basically this is the idea. If you can convert a sine wave like into here, and then you can convert maybe another, like let's say your relation increases the frequency, and then this will go into like that. Maybe the frequency domain increases here. So can y'all see that if you were to do in the time domain, it's like super difficult to, like, what's the relation here? What's the relation? We don't really know. But once we go into the frequency spectrum, it's like, aha, it's just a rightward shift. Frequency is easy. Yeah. Okay, so this is an example of how a latent space prediction might be helpful because you can predict things in a much simpler way if you can represent them in the right space. So the trick is the right space. Okay, how do we know what is the right space? So that is an HO problem. I think deep learning has tried to solve it using some like of this kind of joint embedding architecture where you try to minimize this loss, like typically L2 loss in the latent space. Okay, and this kind of thing could help to like unify both encoders to encode the domains in the same part. All right, so that's one way to do it. I think this is what deep learning is doing. Perhaps there's another way to do it. All right. Increasingly, I've been thinking, okay, so this is my view, all right? Increasingly, I've been thinking to go into latent space. Maybe you don't need to learn the mapping. Maybe what is already there is the structure has already different levels of hierarchy that is all inbuilt, all rules-based. And then at each level of hierarchy, then maybe you learn this encoding at each level. So there's a certain rule base to like like help you zoom in from big image to small image. There's a certain rules thing that is encoded. And then within that rules, then we can learn maybe this joint embedding. So increasingly, I've been thinking this way because like it's very, very difficult to learn a latent space from scratch. There must be some guidelines. Right? So I mean, we can discuss this more later, but I'm not going to go through too much of that because that's all my views right now until I code it out in some experiments. Then I'll let you all know again whether it works out. Okay, so this joint embedding predictive architecture is quite useful because if we can do things in latent space, it's more natural for prediction rather than, this generative architecture, you convert back from latent space to pixel space. Lots of things can go wrong. All right. So yeah, I mean, this kind of works for token generation somehow. Okay, because the token generation of transformers, there's only that many tokens. So you can do this kind of prediction for transformers because the chance of going wrong is much less. But if you have 255 times 255 times 255 pixels, or you can also times another 255 for transparency, or 256 if you like to count the zero as well, that is just insanely a lot to predict. That's too much to predict. So this generative architecture back into the pixel space for images is not feasible. So people would want to go into I-JEPA here. Okay, so I took quite a long time to talk about this because I think this is a very, very important concept. This latent space cannot be neglected. I think a lot of advancements in AI will come from utilizing this latent space better, finding better latent space to predict it. Okay, so as what you can see in the paper, downstream tasks of I-JEPA consists of like ImageNet classifications. This is not shown in the paper, but you can also use this to make decisions. Like decision making can be from this latent space representation. You can then do some form of like MLPs or so on. Like this can be used in reinforcement learning as well. Yeah, you can do predictions with this representation. In fact, this clip has been used in reinforcement learning as well for image and text. They use image clip and text clip, and then they can get the robot to like navigate from one part of the room to another part of the room. I saw this in Europe 2022 when I was there. So this already has shown to be useful to do prediction in latent space. And I think this is really quite important. All right, so latent space. All right, so before we move on to I-JEPA, I'd like to just touch on latent space and how cool this idea has been used in this very, very cool thing called stable diffusion. All right, so I'm not going to cover the full thing of stable diffusion. I will have another session to talk about that. But one good thing about stable diffusion is they didn't predict the pixels, all right? They predicted in the latent space. So like, for example, this UNet, what they do is they try to remove noise in the latent space, okay? So they have a noise parameter, and then how much noise to remove is set by you. The more noise, the more drastic the image can change, okay? So you remove noise, so you start with a garbled piece of noise here in the latent space, and you slowly remove and remove and remove. And once you, okay, so this is actually not in the latent space, this is actually the pixel space already. But the noise that you remove actually is in the latent space. So as you remove more and more noise in the latent space, you kind of get a clearer and clearer picture. All right. So at the end over here, you can see like from a garbage piece of noise here, the image has already gotten to the part like this is like maybe a river or something like that. Yeah. So of course, this needs to be guided by some text prompts. And this guided by text prompts part will feed into this latent space. So let me just show you a rough diagram in the next part here. So if you see here, this is how like stable diffusion works. Okay, you currently have like a text here. This text comes in here, okay, and gets encoded into a latent representation. So this is the latent encoding of text. And the very, very cool part is that from this garbage noise here, okay, what will happen is you will keep doing this transformer kind of architecture where the keys and values come from this like text, okay? And this, I mean, this can also use other conditioning, like you can do, you do control net, you can actually condition more things like that and other things. Yeah, so you can condition on more things, and all this will get fed as the key value here. And this garbled noise will be the query. So this garbled piece of noise here will get refined better and better after each cycle. It gets refined to be closer to the conditioning. Yeah. So And all this is done in latent space. So you just repeat this many times, you get a clearer and clearer image at the end. So this is something quite cool, because if Stable Diffusion had done it in the pixel space, the image will be very blurry. But because they did it nicely in latent space, when you convert it back using a decoder, okay, this is the decoder, we convert it back into the pixel space, this decoder is quite clear, right? So of course, how to train this encoder and decoder, that's a different issue here, because we need to basically map every single piece of image, okay, into a latent space, and need to map every latent space back into an image. So this, they use an autoencoder, and this one here is trained separately from the diffusion process. So I think the idea of like trying to get things done in the latent space, and then, you know, if you kind of want your use case to go back to pixel space, then you train like some sort of like autoencoder or generative method to go back to the pixel space. I think that is working quite well. All right, so I have something to chat. Let's take a look. Hi John, would you consider stuff like Fourier transform and LOG filters to be representations of pixel or latent space? Okay, sorry. Can you elaborate what's an LOG filter?
Hello.
Yeah. Hi.
Yeah. It's like you know, like the image, right? If you I think LOG is like you filter for edges, so it's like edge map. Yeah. So the LOG kind of still looks like the image. But for Fourier, it usually looks very different. I'm not sure if you're familiar with the image Fourier transform. Like I think usually for MRI. Like after you do the Fourier transform, everything will be radiating from the center. So it's still a kind of a pixel representation, but it looks very different from the original image.
But does it look like the image original is different, right? Quite different from the original image.
Fourier is completely different.
Yeah. So stuff like Fourier transform can be a latent space. Yeah. LOG filter, I have to see what it is before I can give you an answer. Yeah, because if you can actually manipulate your image better in the frequency domain, maybe somehow the image itself, like if you transform into frequency, I guess it takes into account the various neighbors of the pixel, right? When you do the frequency component. Yeah, if that is a better representation and you can manipulate on that, then yeah, that will be a suitable latent space.
Okay. Cool.
A lot of things, yeah, no problem. Yeah, a lot of things can be latent space. Okay, but not every latent space is good. Latent space is a very misused word. Like you just pass through an MLP, we call it latent space already. Like that's just like everything is a latent space in that case. In a deep learning model, you just take any layer, that's a latent space, right? So that is something that is quite misused quite often. But in this case, we call this the latent space when it can be useful. All right. So again, this is very like arbitrary. But if you can find a right way to encode and decode into a suitable space here, that ideally is of a lower dimension than your original space, because if not, you might as well do in the original space, right? Yeah. So if you can go in the lower dimension, that is easier to process, then yeah, that it can be a latent space. I mean, some people have experimented with the latent space being higher dimensional, and you know, they say that it can be sparse and it works better. Yeah, sure. Yeah. So we haven't solved this problem yet. So this is an open question. No one knows what's a good latent space. Okay, we just trying different architectures, and then if it works, then we call it latent space. Okay, so I might be like dismissing this a bit too much, but I really don't think anyone has a good idea of what a latent space is. Yeah. So, and I'm starting to think that maybe deep learning approaches won't get you that latent space. At least that's my recent thoughts. Yeah. Okay, let's move on. Let's move on. Okay, there's quite a lot of slides today. And before I go on to I-JEPA, let me just take this moment to do something I really wanted to do for my past few YouTube sessions, which is to talk about how I dislike vision transformers. All right, so we're going to talk about vision transformers and also the improvement to vision transformers called Swin Transformers. We're going to talk about this because actually the encoder and the decoder, or the encoder for the JEPA model, they use a vision transformer. So I was actually quite happy with the I-JEPA paper until I read that they use vision transformers. Then I was like, why? Why did you use a vision transformer? Okay, so let me explain why I think it's not good. Okay, so let's take a look at this. The bear on the left and the scrambled bear on the right. Do these two have the same meaning to you? Anyone? Like, will you be able to recognize like the left picture from the right?
Generally.
Sorry?
Generally, yes. You can tell they're very similar. With enough time and effort, you can put them back together again. But you can see at first glance, they're clearly different. Right? They've been rearranged.
Yeah, thanks for the response. Yes, they can look the same to you because there's only 4 squares. Okay, if I scramble like 16 or 32 squares, I think the human vision would lose its capabilities. Okay, that we can do an experiment, but I don't have the slides right now. But yes, you can try to piece them back together. But if I didn't tell you which one is the original, okay, I'm quite sure if I give you this picture here, you'll be like, what do you just give me? Like, what do you just, if you don't have this left side as the conditioning, you'll be like, what's this? Yeah, then you'll be, hey, how come this picture doesn't make sense? This head gets chopped off here, you know, there's some weird details missing. So that is at least what I would think it is. And for vision transformers, these 2 views look about the same. All right, I mean, they get similar accuracies based on classification of the ImageNet dataset. However, you might say that, okay, maybe ImageNet is very high resolution. Maybe you just take a look at this, you can classify this as bare. All right, I don't really need to look at the whole image. I can look at part of it and classify it. And yeah, sure. But what I'm feeling is that the spatial dimension in the vision transformer is not really preserved. Okay, let's take a look at what the vision transformer is. So a vision transformer is like what you saw just now. Okay, the high level view of vision transformer is like that. You take an image, you cut it up into slices. Okay, in a vision transformer, what they did is they did 16 by 16 patches, but this patch number is configurable. Okay, so you just take these slices, and guess what? You don't even put them in 2D. You put them in 1D. You just take the slice, you line them up like a token. Okay, like each slice of this image is one token. Is like, for example, in text, this can be like, I am a student, you know, that kind of thing. You just slice the image up into patches, and then each patch you just put there, and it completely messes up with all the horizontal. I mean, horizontal maybe yes, preserved in a limited extent because like you still preserve it like that. Yeah, the vertical part all gone. All right, and they realized in the experiments for vision transformers that they use one-dimensional position embeddings, which is using the sine and cosine embeddings like that, or they do two-dimensional, which is like this column and row. They realized that the 2D and the 1D positional embeddings make no difference at all in the accuracy. It's still like 63% accuracy in the ImageNet classification task. So that is something that should surprise you. Okay, it means that no matter how I rearrange my pixels in the rows and the columns, you know, it doesn't really make any difference in the output. So is vision transformer really preserving the spatial details of the image? Not really, you know, not really. Okay, the patches over here, as I mentioned over here, you arbitrarily cut them off, okay, and you linearly embed them. So this is actually even worse. Okay, so in the back end of this linear project, this is what happens. You have an image like that. Okay, let's say this is your patch over here. Your patch maybe consists of like maybe 3 by 3 pixels. What you do is you flatten it out like that. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, flatten out into a linear vector, and then after that you just proceed to do like an MLP.
I was going to say, but the MLP in effect reconstructs the relationships.
So sorry, say again.
In effect, the MLP will reconstruct the relationships.
If it knows where it comes from, because MLP by nature of it, it doesn't have any spatial information. It doesn't.
No, it doesn't. It doesn't have spatial information. It has ordering information. And so, and because they're flattened using the same algorithm, one assumes, then implicitly they will have relationships through the MLP. I'm
not sure if I can agree with that, you know, because like I don't really know whether MLP has any mechanism to preserve like node 1, node 2. I mean, MLP is okay. Yes, I guess because of the weights, right? The weights coming out from each node are the same. Like, so perhaps they can pay special attention to certain nodes through some like, maybe like this X1 is slightly different from this X2, and then later towards the end, you could decode the position using the weight.
Well, yeah, in terms of, so once you pick up this flattened linear components, right? Now we know, because we know where it came from, because the algorithm, that let's say, elements in your original 3x3 grid, the elements 1 and 4 happen to be next to each other, right?
Okay.
So when it comes through the MLP, they'll often have a strong relationship one to the other, just because that's where they came from, right?
That's provided that the algorithm knows that these are semantically related.
No, not even. It's just because they came from an original where they were next to each other. And so they will tend to, over time, over many images, they'll tend to have a higher relationship one to the next.
So I think you make a good point here. With enough data, maybe you can learn this weight such that the weight itself embodies some of the position. Is that what you're saying?
Essentially, yeah.
Yes. So I'm saying that that's exactly what we see in vision transformers here. When they are trained with a super mega large data sets called the JPT300, which is much larger than ImageNet, I think 1,000 times larger. They do very well. They even get 99% accuracy on ImageNet. Yeah, but if they are trained on just ImageNet alone, their performance is actually not as good as like just a CNN. So we can see that just by asking the model to learn everything. So I buy your point. You might be able to embody the position if you train long enough and your linear layer weights learn some patterns such that in the later layers, they can decode that these two patches are the same, or these two, like even this flattened layer, these two pixels are the same, in the same proximity. Yes, maybe we can do that. But it takes a very, very long time to train, okay, to learn all this, very long time to learn all these implicit biases.
Sorry, can I try something?
Yeah.
Is there any experiments doing something like they randomly permute the sequence, then they still have the same level of performance?
Okay, that I'm not sure. But I do know the experiments that remove away the positional embeddings and get about the same performance.
I see. So
yeah, the random permutation one is an interesting one. Maybe if we take an image and randomly permute, but as what was mentioned just now, maybe the linear layers already have some implicit positional bias. Yeah, I didn't think of that.
I guess that can tell you whether it really works with that in that way, right?
Yeah. If you take a scrambled image and it still gives you the same, then this implicit bias doesn't really matter, right? In the weights.
And also even in conv nets, your last layer is doing similar things, right?
True. Last layer they flatten everything. Yeah.
Yeah, and I don't know if that matters or not. So if it works really in this way, by which I mean that it kind of has the proximity by the neighboring what do you call it, the neighboring nodes, then it represents something nearer to each other, then yeah, I think it's the same thing. Yeah, we just need to run some experiment to check.
True. I mean, it's quite interesting. Have you heard of this architecture called the MLP mixer? So apparently you don't need convolutions, you just need a series of MLPs, and then you take the row, you take the column, you take the depth, you permute the image in various ways, you pass it through various MLPs, and it performs just as well as ConvNets. Yeah, so I think this MLP mixer is quite fascinating. I have no idea why it works, but maybe what mentioned here, maybe this is the reason why it works, because it can learn implicit positional bias. Okay, but I would like to say the same thing. It takes a long time to learn this implicit bias. If you can pre-build this bias in, you can learn with much fewer data. You know, it's like if I can tell you the structure of the sentence is like 5 words, you don't have to learn that it's 5 words, or you don't have to learn that M comes before M comes after I. If I tell you like, okay, this is the structure, I M is together. Yeah, so it basically, if you have this kind of implicit biases that hold true all the time, why waste time to learn them, right? So I mean, I'm of the view that efficient learning comes with enough implicit biases. So vision transformers of the view we should remove all these implicit biases and we'll do well. MLP mixer is extreme, okay? It's like everything should just be an MLP. Yeah, so this is some of the recent advancements which I kind of disagree with. Yeah, because like just because you can feed in a load of data in doesn't mean you should, right? I still like the idea of spatial invariance in CNNs. Right, so if you can see my point over here, the loss function in this VIT is not the next token prediction. So this is just using, okay, they're just taking one of the output, like let's say this is a token, right? The token embeddings here, once after you linearly embed, after you pass through here, the linear layer will embed it. This embeddings will then go through like cross attention here, okay? And this few attention layers at the end, what will happen is it will go through to the end. You just take the first token. Okay, so this is something like a bird kind of transformer, right? Where you have it's actually, if I'm not wrong, is not mass transformer. It's like all tokens can attend to each other. So this means that what they did is that they just said, okay, I'm going to ignore all these tokens here. I'm going to say that all these tokens at the end, these are not needed for the task. I'm only just going to take the top token here, and then I'm going through MLP in order to classify it into like what image class is it? Is bird, ball, or car? So I mean, this is fine, okay, because like, you can just stick any, like, it's been shown that like for transformers, you can just attach like maybe a linear layer and then you can classify it. So this is exactly what it's doing. It's like attaching a linear layer to do a classification. Like this is what bird has shown as well. You can just take the encoder and you can just classify it. So this thing here is very, very, very similar to bird, all right? But the problem with this kind of way is that this transformer here, okay, let me just say this transformer here in bird, okay, the transformer is trained on next token prediction. In the vision transformer, this is not done at all. You're just taking the transformer architecture, feed in the image patches, and then you're using this classification loss to learn the entire transformer structure. Okay, and that is inefficient. That is really, really inefficient because you lose out on like the pre-training part of the transformer. So this is something that like, okay, this is something that I don't agree with. Like I really don't think this patches thing is very natural for images. And like, in fact, when you do it the patches, you can even lose out certain information. Like for example, if you have a face over here, or you have a circle here, if I cut this into half and like that, what you will see is like quadrants. Okay, you might even not know that this forms a circle. So stuff like this would be one of the problems with vision transformers. It's like you arbitrarily cut your input slices. So I don't know. I kind of still prefer CNNs. Okay, so this is my take on this. Oh yeah, before I move on, anyone wants to talk anything about vision transformers? If you are a supporter of vision transformer, now is the time to sound out.
Okay, so I know some works they probably has done some. Actually, I don't know. It's just an idea. Maybe someone has done it. So this part, as I just mentioned, right, is really parallel to the last layer of CNN, right? Then why don't you just use you prefer the what is it? The inductive bias of ConvNets, right? Then you use that to do some pre-processing. Then after that, you fit into transformers. Since I mean at the last layer of CNN, you have the same thing. So
yeah. So actually that idea I still buy. There's one thing called conv mixer you can try. So it's exactly what you're saying. Use a ConvNet to do the token embeddings. But the problem is the ConvNet is still done on the patch itself. So you lose out the inter-patch area. Your whatever information you get is just based on that single patch. Yeah, so I think this is something that people are exploring right now, like how to better do it.
I think so long as your number of patches at that point is not too many. It's like the example you show is just 4. If it's just 4 patches, and probably won't lose too much information.
Perhaps. Actually, I'm just thinking whether or not you could do dynamic patch sizing. Like you do bigger patch to smaller patch. Then at least the bigger patch might capture the inter-patch stuff that you slice later.
You mean like at the region or the boundary where the information is more crucial?
Yeah, no, it's more like how we slice it. I mean, I think it's okay to slice information if we have the in-between regions preserved somewhat. So like, for example, you can take an image and you can slice it into 4 parts first. Then maybe another layer, you could process it with 16 parts. So, what I mean, like at least the broad picture is preserved at some layer in the image. Yeah, so anyway, the extension to Vision Transformer, one of the most popular one is called the Swin Transformer. And the Swin Transformer actually does quite a lot of things that I like. Okay, but it doesn't do them in the right way that I like it. Okay, so the Swin Transformer is hierarchical in nature. So like the Vision Transformer through the layers, you have 16 by 16 patches, and then you do self-attention globally across all patches. Okay, so the Swin Transformer, what it does is that you actually split. Okay, so this is like the patches here, right? You can see that the patches come in different sizes now. So this is the idea that I like. So if you can take your image and then you have varying sizes of patches, you might be able to capture the inter-patch area here. Okay, I mean, that's if you want to use patches. Okay, I mean, kind of think of it actually like CNN is kind of a patch. So like, I mean, but the patch can be applied globally. It's not just like, because the filter applies to the whole image. This patch, unfortunately, the processing is just done in the patch itself. Okay, but Swin Transformer, the idea is that you do like attention that is like sustained within this patch here. And then what you do is then you do have a way to combine all this into like a smaller patch, like here. This mechanism of a patch merging, okay, to merge a smaller patch into a like smaller patch into like one patch, and then you can like do this all the way until the top. So this basically processes the image at a more fine grain all the way to the more broad grain. All right, so this is actually I think it's a better way to process stuff, because like at least you have some hierarchical way of prediction. All right, and this actually performs better, much better than Vision Transformers. Hierarchy, okay, hierarchy is very, very important. I think we should see more of this kind of architectures. But my point of view is that the order is wrong. All right, most of the times when humans think of a scene, okay, we look at the scene and say, okay, this is a beach. Then I see a frisbee come. Okay, this is a frisbee at the beach. Okay, imagine you do this here, then it's like you are saying, okay, you have a red this, then you can see like sand and stuff. Then after you go up here, this is like beach. Then when you go up here, it's like dog and man at beach. Yeah, but you know, the thing is, sometimes the very specific things you see, okay, is actually conditioned on the top stuff. Like most of the time, the specific stuff is conditioned on the broad. So I think this is done wrongly. You should do the conditioning at the top first, and then you use that to do the prediction for the bottom. At least that's how I think as well. Like when you go into a room, you first size up, okay, what kind of room this is. Then the objects you see in this room will have different kind of interpretation based on where do you think you are. All right. So, okay, we can leave this to the discussion later, because I have a few slides on this later. Yeah, but I do like this hierarchical part. Yeah, I do like the fact that your patches can dynamically scale. Okay, unfortunately, I-JEPA did not use this. So, yeah. All right. So Swin Transformers also have another thing where they try to shift the global attention using sliding windows. So like, for example, in one layer, you not only pay attention to like this patch here, you also pay attention to the middle patch here, and you also pay attention to here. Yeah, so this is something that is, I think, quite cool. Like, you can also do, this is how they did it. They just did like, oops, sorry. The mask just shifted down like that. And then they do a cyclic fill up of the rest of the areas here. But all these areas here are masks. Okay, because all these areas that you like kind of plug and play into this square here, like you drag and drop and put here, this do not belong to the original part of the image. It's like the top of the tree go to the bottom. You don't want this square here to learn this relation. Okay, so you mask it out. So within each square now you do the global attention. So in some sense, you can treat this as like trying to learn like various informations within like this kind of like basically you are trying to do a global attention in a different way. It's just a shifted attention method. Yeah. So just another way of doing it. But okay, this is not the main point. The main point is this. Okay, this is the main point. I think we need more of this kind of architectures. I think maybe that will be the next step for I-JEPA, to do a hierarchical kind of I-JEPA. Okay.
Sorry, I just want to clarify. Can you go back to the previous slide?
This
Yeah,
one? This one.
no, the first slide of this one, yes. So the top one, right? So the attention is applied for every single pixel within one patch, is it?
Yeah, the attention is in the red color square. So all the patches are the gray squares here. So attention will be globally across all the 16 patches.
Oh, so by within one patch, there is no attention happening.
No, you don't pay attention. A patch is like a token, you see. So you do attention across tokens.
I see.
Yeah.
Yes.
Okay, so the main thing why I wanted to talk about the Swin Transformer is because they showed this thing that I wanted to highlight. They took away the positional embeddings, absolute, relative position, no position embeddings. You look at the accuracy difference. It's almost the same. Yeah, so you can largely ignore the positional embeddings. And VIT and this Swin Transformer, the architecture is similar because they do by patches, right? If you can ignore this positional embeddings, it means that actually why do you bother encoding in? Because like it doesn't look like it makes a difference. And it also highlights to me that this is probably not a good way to process images because you lose all this spatial information. Okay, this maybe because like as what that's what Richard was saying, you can actually learn, like the MLP can actually learn the positional bias. So maybe that's the case. Like you train long enough, maybe that's the case. So yeah, maybe so. And maybe you put in the positional embeddings, you can learn faster. But still the difference is not much. I don't think this is a very natural way of like imbuing like stuff like translational invariance. So I'd like to see a better way to do attention, and that doesn't involve patches. Okay, but enough ranting about VIT. I think now is a good time to go into the main architecture of I-JEPA. So what is I-JEPA? I-JEPA is basically VIT applied as the context. So they use the VIT patch idea. Okay, the context, you see like this dot over here. You give a certain part of the dot as a context. Okay, like for example, this is the thing that the encoder sees. The rest are masked out. Okay, so given this as the context, what I want to do is I want to kind of predict like what are my different boxes. So remember earlier on we talked about a variable Z, which you can use to condition. This Z is actually the position. The latent variable is the position of the box of the patches to be predicted. Okay, so with this in mind, we then predict the latent representation. Like let's say if you talk about this blue square, you take this blue, you know you want to predict this, you predict this blue square here. All right, and this is basically done by the predictor. The predictor takes in the latent representation of your context and predicts a square, okay, or predicts a region that is defined by your latent variable. And this region here, you have the ground truth, which is like this dot, the top part here. And you can do for different boxes, all right? And the key thing to note is that this whole thing is self-supervised learning, okay? Because this context and target do not need human labels. So I like this part. I like this part a lot, okay? Because all along we've been struggling, when you try to do mass entity prediction in an image, okay, we've been struggling because the image outcome becomes like super blurry. Here, I-JEPA's purpose is not to get back into the pixel space. Okay, it's not. Okay, I can tell you the purpose is not. They are trying to predict from latent space to latent space. Given this latent space here, predict another latent space. So the prediction is purely latent to latent. Prediction is latent space to latent space. Okay, and that's exactly like a similar kind of prediction that Stable Diffusion does. So this very similar to Stable Diffusion. Okay, but the difference between Stable Diffusion is that this learning target is it can be learned through self-supervised learning. Like, in fact, Stable Diffusion also learn through some form of self-supervised learning because they just add noise and train on the noise they added. So this one, your context and your target, the image is the same. You just mask out certain parts for your context. Okay, so again, you must question, is this really context? Because when I think about context, it's like more like a broad view of the thing, right? Now what you are doing is you are taking one part of the image and you're predicting other parts of the image. It's more like mass patch prediction. So I would think of context more like maybe you talk about like a picture of a dog. Maybe the context can be in words. I think this hasn't been explored yet. Why can't you use like maybe this part of the picture and say like what you think this picture is? And then you can use maybe this word to condition. Okay, so this again is my idea already. Okay, you can use this text here to condition the latent space, because you know you can have clip, you can condition this as the latent space. Okay, and maybe you can predict better, because Stable Diffusion does that as well. You can use text to condition your latent space. If you encode again your encoder here, okay, you must do some joint encoding so that the encoder here and the encode, this is encoder for text and the encoder for images. Again, this must lead to the same latent space. Okay, but Stable Diffusion has shown that this can be done. So this may be a possible extension to I-JEPA. Okay, but let's erase that for now. I don't want to confuse you all because this is not I-JEPA. This is my view. So I-JEPA, what it really does is it takes patches of the image and it predicts other patches. And from the latent space here, what you are doing is you are just checking the L2 distance. Okay, later I'll show you the loss function. So I like the training process. I like this training process a lot. It gives you unsupervised training or self-supervised training. Your objective can be found from the images you find on the web. All you need to do is to do some masking of the image, and then you can predict the mask components. Okay, so this is pretty similar to like mask token prediction in BERT. You mask out like 15% of the word tokens, or mask out 15% of the tokens and try to predict those 15% of the tokens. Okay, so the problem with this, okay, is that like the given like context over here, again, you might lose out like certain stuff on like the continuity of the image, because you know, if you use VIT, does not respect the spatial geometries of an image. Yeah, so this I think is good for like a good first cut, but I hope in the future they don't use VIT. I mean, why can't you just use if you really want to do the context, okay, why don't you just like make the image blurry or something? Then you try to predict the blurry parts, you know, and use a CNN or something. Yeah, I mean, why use patches? Why not just do the whole image? Like, or maybe you have a way to mask out the image in the original CNN without using patches. Like, then you can process the entire image as one go without using patch. Yeah. Okay, so anyway, this is how I-JEPA works. The key idea is like that. That's why I explained. Like, whatever patch you see, okay, the area outside this, sorry, whatever blue box you see here, the area outside is given as the context, okay, fed into the VIT, okay, to get a latent space, and you try to predict the area inside this blue box in the latent space. Okay, but then you might ask me, you know, how did we get these sketches here, right? How did we get the sketches if we don't have the pixel space? So what they did is that they took the latent representation and they took the original pixel space and they learn a generator model. So the generator model will know the original pixel space, what's there, and they know what's the latent space. They try to map from the latent space back to the pixel space. So you get back this like maps here, which if you look at it is actually pretty good. I mean, it kind of gets most of it right. Again, you can see that the way that the prediction is done here, because you know it doesn't really respect the spatial geometries of the image. You can see that the prediction here, like, is not exactly aligned. You see, like, okay, actually this is not bad. Actually, all these predictions are still okay. Yeah. So yeah, I guess this I-JEPA is not too bad after all. But I hope we can find a better way other than VITs to do the encoder. Okay, so what you can see, this is the original paper in Yann LeCun, this path towards autonomous machine intelligence. This is JEPA with two different with the same encoder. You have a predictor. So essentially, he has implemented this whole thing for images, except this part here, this part, and this part. Okay, so my opinion, these three parts I also don't think is necessary, because in order to find information content, you need to use some form of like probabilities, and you know, probabilities can be very hard to, it can be intractable for very high dimensions, because the probabilities can be like over like a billion or a zillion kind of objects, or basically it's very hard to do this kind of information content with probabilities. He tried to do this, Yann LeCun tried to do this using big rec, variance, invariance, covariance, regularization. Yeah, I think it didn't work out too well. That's why it's not here in I-JEPA. So I quite agree with the way I-JEPA is doing it. Take away this information stuff because it's really hard to compute those. And honestly, you may not need to do this. Why did he want to do this information content? Okay, why is to have a why maximize information content in latent space is actually to have a more compact representation. Okay, so this is how I put it. He's trying to get a latent space that can more succinctly represent the input space. Okay, and I think one part here that is missing is that the latent space itself should have like less like complexity than the original space. Yeah, so as you can see here, we haven't quite figured out how to get the latent space yet. Okay, so what I think is that in order to get the latent space, may need some form of rule-based hierarchy generation. Okay, so now is the time to talk about all these ideas that I have. Okay, so this part here has shown that like we try to do prediction latent space, but we kind of don't know how to get the latent space. Like how I-JEPA did it in the latent space is through doing this L2 loss in the latent space, and then through that you also learn how to get this encoder done. All right, so this is how it was done right now, and you can see how useful the approach is. Okay, this is just the loss function. It's just the L2 loss in the latent space. Okay, so talking about latent space now, so this gets me excited. I-JEPA, you see, it doesn't learn how to get into the latent space directly. It learns through backpropagation of the L2 loss of the basically the latent patches that it generates, how close it is to the original latent patches. And you can say in the paper that it said that it's computationally efficient. And you take a look over here, look at this. It's 1,000 pre-training hours, quite efficient, right? 1,000 hours. I think that's not too bad, right? I mean, just a few days. I don't know. 1,000 is how many days? 1,000 GPU hours is maybe a month, 1 or 2 months. Yeah, so this is actually not very efficient if you look at it. In order to like match like ImageNet benchmarks accuracy of like other models, it takes weeks of pre-training GPU hours, and that's not good. All right, that's not good. So you might say that, okay, yes, this is the pre-training step. Okay, when we come to fine-tuning on ImageNet after the pre-training, we just need 300 epochs. Not bad. Yeah, that I can buy. Yeah, but again, like most of the vision transformer models, it just takes very long for the model to learn something, right? Because a lot of the biases of space is not there. You have to learn from scratch, right? A lot of in I-JEPA, the latent space itself is learned from scratch. So, there's this problem of latent space shift. Okay, so let me tell you this problem right now. Okay, imagine if I were to tell you a language like A goes to B, and like AB goes to C. So you've been learning this language from day one, and then suddenly I tell you, okay, now AA goes to C, and AB goes to D. If I suddenly switch your language, and then you have to learn this again, right? Like it's very disruptive. Like if I have to learn both this forward direction arrow, and I have to learn how to interpret this thing with like maybe the outcome here, I have to learn two things. Learn how to map input to latent space. And the second thing I learned is how to map latent space input to predicted latent space. So there are two objectives we need to learn here. We need to learn both how to map into the latent space, and when we are in the latent space, how to predict. Okay, so this, you can see a problem here. You change the mapping, you change the learning. You change this learning thing, you might need to change the mapping. So it's like two dueling objectives here. And that's also one of the key reasons why I think that the latent space, perhaps it shouldn't be learned like that. Okay, it should be learned with some rule-based method, or you learn the latent space first and you freeze it. Okay, like a clip embedding, you freeze the clip embedding, you don't touch it. Then you learn this latent space prediction. Okay, stuff like this, if you use a pre-trained encoder and for the context, maybe you will learn way faster. Okay, you may not need 1,000 GPU hours. Maybe you can learn within 1 day. Okay, so this is why I think I-JEPA fails at. It's trying to learn too much with just one objective. Okay, it is much better if we learn the context encoder and decoder maybe through an autoencoder, like what Stable-Diffusion did. Okay, so these are stuff that I think could be done, or you could have a rule-based way to learn this encoder. Like you could encode it by saying that, okay, I consider patches of this size, then I consider patches of another size, you know, something like that. Yeah, need to think more about this, but you can see that this way of training, I like the idea of self-supervised learning like that in latent space, but the idea of getting the right latent space and the idea of getting the right prediction using just one loss function like this has led to a very, very inefficient learning. All right, 1,000 GPU hours. I mean, that's fine for meta, but that's probably out of reach for a lot of other people, right? So one good thing though about I-JEPA is that you don't need to use data augmentations to do contrastive loss. So like other contrastive methods like bring your own latents and VigRec, this actually what they do is they take a certain image, they apply a certain transformation A and transformation B, like maybe a translation or rotation. And then what you want to do is you go through some processing layers, and then at the end of it, you want to see or not whether or not it's the same. So you have a contrastive loss here. Yeah, so if let's say you have a different image from the top and the bottom, then you will say that the loss is either same or not same. Yeah, so this is a binary loss. So this contrastive loss uses a lot of data augmentations like translations, rotations, data augmentation, other data augmentation techniques, skewing, yeah, those other stuff, which actually take a long time to train because you need to do this various data augmentations. I-JEPA doesn't need to, because I-JEPA doesn't do this contrastive method. I-JEPA just do self-supervised learning. I think that's a huge win for image domain. Okay, if we can do self-supervised learning like this, like I-JEPA, you unlock a lot of potential because self-supervised learning can be done over the entire internet's worth of images. And this is a very powerful idea. This is exactly why transformers did so well, because they can learn from the entire internet's worth of text. Self-supervised learning, I think this is a very powerful idea in AI. And I'm very glad I-JEPA did this. Okay, but what I-JEPA could do better is use a better encoder other than VITs. VITs really shouldn't be used, all right? And yeah, perhaps what they can do is they could use a fixed encoder and just learn the prediction loss using this. So you don't learn both the encoder and the prediction loss. You just learn the prediction loss with this loss function. I think this will make I-JEPA perform much better. Okay, let's compare and see like the CNN network, all right? This is using CompNets only. And you see, this is EfficientNet v2. EfficientNet v2, what they did was they have a graph here. The training time is like less than 1 TPU day. It's already for 84%. Okay, let's compare and contrast. All right, so they only show us this graph, right? You can see that if we talk about EfficientNet is here. Yeah, so I-JEPA isn't that great after all. I mean, it's not as good as models trained like directly on ImageNet. And this trains much faster as well. So there's room for improvement. And I think the room for improvement is to not use VIT. Okay. So you can see that this like EfficientNet v2 like is much better than, you know, like VIT training many times, and VIT just still not it's like about the same performance as the starting of this EfficientNet. So I think this is an indication that VITs are just not very efficient to train. Right? So even this is data efficient transformers, right? You can see that the parameters are so much, but the performance is not as good. Yeah, so that's a food for thought, all right? What we see from meta side is it wins other variants of VITs. Okay, but what we don't see is that in the large scale of things, actually this VIT is not that great, at least for efficient learning. So these are some of my thoughts, all right? So in order to get a better representation space, right? So this representational like space is actually otherwise known as the latent space. I mean, everyone using latent space, but no one really knows what it means. Right? What this latent space ideally should do is it should process information at an easier way at an easier way so that you can get the output much more easily. All right, so it's like the sine wave, it's hard to process in time domain, so you use the Fourier domain, the frequency domain. And it is my belief that fixed biases like translational invariance in CNNs can help to speed up this learning. Because like in CNNs, your filters, you learn one filter you can apply for the entire image itself. So whatever you learn, like how to identify a dot on the top left part of the image, you can learn for the entire image how to identify a dot. For VITs, you need to learn that separately for each patch. So that's not exactly very efficient way of learning. Okay, so, and I also believe that like for most intelligent purposes, like you don't need to go back into the input space. Okay, input space is like if you want image generation, a very difficult problem. But if you just want to use it to do decision making for agents, which is my interest, you don't have to go back to the input space. You can just use the latent space and continue go downwards for downstream tasks, like the image prediction tasks. So this is my summarized information pipeline. I think we have more to do with this latent part that we haven't really figured out yet. This part here this should be the focus of future research, I think, like how to get this latent space better. And I'll be covering more of this next time also. So okay, before I move on to my other thoughts, anything you want to ask about what I've covered so far?
I still have one more clarification regarding VIT.
Okay, yeah, please go ahead.
What's the issue is if I treat every single pixel as a token?
You can. Then it will be very, very similar to just applying like one by one convolutions and then continuing from there.
No, but in this case, because you mentioned like the attention is between every single patch, right?
Yes.
So now I have the attention of every pixel to every other pixel.
Yeah.
Isn't that good?
So you have every pixel attending to everything, right?
That roughly already tells you how strongly connected is some pixel with respect to other pixels. So naturally, I guess especially for those patch of pixels that represent the same object, then naturally they should have very high attention with each other, right? So that's already a substitute of something like a kernel in the COMNET.
Yes and no. I mean, it's like using MLPs to do CNN. Using MLPs to do like CIFAR or MNIST. You can use MLP as well. You can have all pixels connect to all pixels. You can flatten it and do a MLP layer. Yes, sure, you can do.
There's no attention in MLP, right?
Yeah, there isn't. Yeah, but you can.
I'm specifically talking about the attention of pixel is other pixel. I mean, that's the most powerful part of transformer. So I thought that should be a good enough substitute for.
How do you get the key and values for your pixels though? How do you know which pixels are related to each other?
Isn't that learned?
I mean, usually the attention matrix, you have to have a key and a value, right? And a query. So like you need the pixel to provide the query, then your key and value needs to. So what will happen is if you go by like maybe the pixel value as your key and your query and your value, your pixel will just like get mixed up with similar colors more often. Yeah, it's a bit tricky because like it's like asking to do attention with letters. Like letter itself doesn't give you much meaning, right? Like classification CLASSI. If you tokenize it by letters and you do attention on letters, does it give you any meaning? Maybe. I get
it, but with larger patches, you are going to have an explosion of number of tokens, right?
Yes, but what they did for the token is that they actually didn't use a discrete number token. What they did for the tokenization is they just skip the tokenization level altogether. They just do a linear embedding. They basically flatten the original input here. No, sorry, not flatten out. They just take the original input, like let's say your patch is like a 3x3 patch, pixel patch, and then you do a multiplication by an embedding matrix to get like a 1/d embedding.
And how is this embedding learned?
Oh, the embedding matrix is kind of fixed. Sorry, it's learnable. The embedding matrix is learnable. So you can learn through backprop. it's very similar to how we do embedding for tokens. It's just that in tokens, for the tokens of for words, your embedding is in an embedding matrix, right? You have like
but it's learned, but it's already fixed at the point of time when you train transformer, right?
Yes. I mean, you can also make it flexible, but for most use cases, you finish your transformer, your embedding part is fixed.
Okay. But but they still map. I mean, there's still many ways to map the patch to the embedding space, right? Because I mean, for what at least it's discrete. Here seems much more difficult.
Yeah, so I think it's not very natural for pixels to be like put together into like a token or like an embedding area. It's not natural. So what is more, I mean, what embedding is doing is actually just to flatten it into a certain dimension.
Okay, but anyway, my main point is if you have a small enough size for your patch, then the attention can be, I think, can maybe powerful enough to replace convolution.
Maybe, yes, maybe. Yeah, if you can have attention, but okay, but there's also another problem here, you see. Attention is based on the sort of the input key and the query. So it would like sort of differ for each kind of use case. Whereas like for a filter, you might be able to detect a dog or cat, you know, that kind of stuff that is kind of fixed. So attention is a bit more dynamic in the sense that it's dependent on the inputs of the layers.
Yes, but you don't know whether it's a good thing or bad thing, right? Maybe it turns out to be a good thing. I don't know. Need to give, I'll think more about it. Anyway, that's my first question. The second one is, so for this I-JEPA, right, how does it going to, because Yann LeCun criticized transformer being only be able to do process text, right? I agree with what he said, that the vision part can helps the agent to learn much more efficiently, but not alone as well. I think the way to go is to merge all the different modality, right? So how does I-JEPA, how can it take care of text? Is it a way to take out text?
So this is where I said about the encoder needs to be trained separately, but so I think this context encoder, and maybe next time if you have a text encoder, you could train it jointly to form the same embedding space. So maybe you have text. So this is something like clip. You have a text, you have an image, and you go through some embedding space here. Or latent space. And then you minimize the L2 distance. In clip, they use contrastive loss, but I mean, you can also minimize the L2 distance of the latent space.
Would it be reasonable, right? So if we had like a keyworded image sort of data set, right?
Yes.
So we're combining here text and images in one data set, right? And then if we use, why can't they use, say, separate encoders for the text and images potentially, and then have the predictor operate across both or either potentially? So the idea would be that if you're able to do that, you can use the same sort of masking to do image or text-based prediction, regardless of if they're using the same encoder, because they're using the same data set. You might then have a very powerful technique, because you could take your content encoder for text and push it into an arbitrary large language model then. Right? And the encoder is suitable for that. So you then have a much more, because to do stable diffusion has a very limited vocabulary. It's a very weird vocabulary, right? It's all about image sharing websites. It's the language they use. And so if you are able to have to learn the relationships, because you're using this same source data set, you might be able to then use a much richer language to describe your images, and vice versa. Because there'd be nothing particular to stop you taking an image and, say, using a language model how does that feel?
So
And then get.
Yeah, talking about generating the text using a generative model from an image.
To try and mix up these two, like you're saying, this idea of the latent space being a very powerful way to make predictions. So if we say, take latent at face value, that is hidden, right, unknown, and we have whatever the appropriate context encoder is, and then put the weight on the predictor to understand relationships between them. So this is going back to LeCun's sort of broader theory around layers of abstraction, right?
Yeah, I agree with that.
And I'm just wondering if that would be plausible. I don't think anyone's done it, but I was wondering how plausible that sounds in your head.
Yeah, I was thinking of doing this in fact, that was one of my ideas for one of my projects. It's like I try to use Blip. Blip is the image to text question answer.
Mhm.
I'll try to ask Blip, what is the overall context of an image? Then Blip will tell me, oh, at the beach. Then I'll ask it like, given this, that you are at a beach, what do you see what are the specific entities you see? Then I get back. So basically I use image question answering to like get the details of an image. But I realized Blip is not very capable at doing that. Yeah, but perhaps the training set didn't do this kind of stuff. But I was thinking whether it could do like chain of thought prompting of an image to get the text. Yeah, so I've been toying around with some ideas like that. I think right now the image to text generation is not great. So if you want to do stuff like that, I don't think it's going to do very well. Yeah, unless the image to text generation model improves much better. If not, it's better off to get the text like directly from the internet source, like you do the image tag data set, like what they did for Clip. Yeah, that might be a more feasible approach.
I think there's, when I was thinking about it, I got as far as, I don't know where there's a good data set to work from, right? Because you'd need like, it's clear that what's used in Stable Diffusion, I think it's ImageNet based, it's not sufficient. It gives you very strange language you've got to adopt to get it to work well. And but large language models today are quite rich in the language they can use. So this is kind of where the idea comes from. If you can unify those two, then you might get a little further. But I still think there's not a good enough data set to train on, really, because the ImageNet keywords are so weird.
True. I mean, that's why they scrape the open source image text pair, not just ImageNet. At least that's for Clip. Yeah. So I mean that's very interesting ideas here. Whether it's feasible or not, I think whatever you said, if you can enrich your text and then you can like jointly learn this latent space, yeah, that might work better. Yeah, I do think this latent space is learned before the prediction is learned, or actually it could be learned jointly, but I think something is missing here, because like I do agree. You see, your latent space, if we go back to the first diagram on the car, right? Car driving. Your latent space kind of is based on the task. Yeah, like different tasks requires a different kind of latent space. So I do understand where this is coming from, like this prediction here is, but you do realize that this prediction is not done like that for the task, right? The task is not like just to predict this thing here. The task is actually a downstream task. Yeah, when we actually do actions, the task is actually for some form of decision making. So perhaps the prediction objective of just predicting what will be the next state, that can be done later. But what we need to do first is step 1. Learn the latent space. Yeah, so I don't know whether this can be disentangled from this step 2, which is learn the prediction. But I kind of think that maybe the task at hand, like maybe in this case is a classification task. Like the task at hand might actually guide your latent space forming. Okay, right now what they did here is they do like a transformer self-supervised learning approach, and then you can have different different tasks here. Like you can have decision, you can have classification, you can have object counting, you can have infilling tasks, all from the same model. Just by like continuing from the encoder, you can just directly connect this here, and you can do different tasks. and after some learning. So that's why advantage of this approach. After you finish your context encoder and your predictor, you can kind of just take the context encoder and do different tasks. Yeah. But if you want a more efficient learning of this self-supervised approach, maybe what's needed is the task needs to be given beforehand. I don't know. I'm still thinking about this. Like, it's taking a bit too long to learn this I-JEPA. Like, and I suspect it's because of this dual learning objective of the predictor and the context encoder. Yeah. So I don't know whether what you said, Richard, whether it could help with the learning. Yeah, I mean, you are definitely trying to help to learn the context encoder, right? That if I'm hearing correctly.
Well, I think I'm sort of assuming that there is an effective, if not ideal, context encoder available and target encoder. Right? So, which is a pretty big assumption. Happy to take this, but at the same time, once you're working on and this is a bit I haven't in my head got really terribly clear around is actually that becomes, the first stage of your, take the LeCun thing, this idea of this hierarchy of abstraction, right? That becomes your first stage abstraction. And once it's into latent, that is unknown space, these long vectors, once you're there, then it's just a matter of working on them with essentially stacked predictors until you come up with a result that you like, right? Now, that's some sort of ablation thing, right? But the idea is that the key thing is to get a consistent encoding. That's the thing you can't live without. That must be the case. But it doesn't have to be consistent, I suspect, across domains, because we're going to process it further. Right. So one input gives you one context encoding. That has to be the same all over and over again, because otherwise you can't rely on it from then on.
Yeah.
But you need not have all encodings being identical, as long as they end up in the same context. Then you can find the relationship between them.
I like your idea a lot. Actually, it's very, very similar to what I have in mind. Like your hierarchy of abstractions and then like different ways of generating the encoder, right? Like you need not just have one encoder, you can have multiple encoders actually. And then just let the neural network choose the right encoder for the task.
Yep. Well, or have them fight it out. See which answer you like most.
Yeah, it's like a mixture of experts in some sense. Like you can learn different encoders. You don't have to necessarily stick with one, right? Why stick with one? I like this idea. I like this idea. Yeah, you're on the right track here. Yeah, I hope I understood you correctly. Yeah. So okay, if you don't mind, let me just spend another 1 to 2 minutes to just consolidate the last few slides. So hierarchical prediction, I'll skip this. But the main thing is, I think as what you said earlier, we do have to have this kind of hierarchy of abstractions. And I do think that some form of grounding from high to low level context is needed. Some form of fixed priors is also needed in order to learn with less samples. Like we can extend lines in one straight way. You can extrapolate a pattern like this curve. You can continue extrapolating even though we don't see what's next. We also have memory. So memory is another layer of conditioning that you can do retrieval and you can condition your memory. Okay, and this memory can be of similar scenes, okay, in order to generate correctly the latent representation. So this is something like transformers can do. You can use retrieval augmented generation to do so, right? And this memory can also be in the form of text, okay? All right, text or images, okay, or the latent space representation. So similar to how stable diffusion will do it, your memory that you extract out could be the key and value, and the latent space could be the query. So these are some ideas that I was thinking of. Okay, let's just roughly go through. Like just now, what Richard was saying about the layers of hierarchy. Like I think what happens is that like perhaps you have a rule-based ways to like for image to abstract out layer by layer, like perhaps by size. Okay, by because you have spatial domains, you get top left, top right. So something like patches. Okay, but it's just not one patch. Okay, the patch can actually change size. Okay, and you can condition you're brought to the specific. So perhaps what will happen is that you can condition all the way to the, like in this case, you go all the way to the top here, and then maybe you have your broad category of image, and then you can, after that, you can go down to the specific category of image. And this can be in text, or this also can be using memory to retrieve relevant latent spaces. Okay, so you can see in like this kind of diagram, okay, I'm not really describing feature permanent network here, but I'm just describing how this kind of architecture might look like, because it kind of looks similar to a feature permanent network. Okay, you have the text memory to retrieve relevant latent spaces. You have your broad category. This broad category of image is like your ZAC. So all these are your ZAC in the I-JEPA architecture. You condition on all this and you predict the next latent space. So your predictor takes in this extra information. And all this different stuff, you actually have different layers of abstraction, different layers of latent space. I mean, at the start here, you might even have different ways of encoding your latent space. Different layers of latent space. And then what you do at the end here is you will then do attention across all layers to find out which layers are more important. So this is quite different from I-JEPA, but I think there's something smart about the layers thing, because each layer might attend to different parts of the object. Like the more broad layer might talk about like the frisbee, the top layer might talk about the beach. But in the end, when you want to do like some form of prediction, you might need to use all kinds of information at different levels. And like you also store memory at different levels. So yeah, this is kind of my view of like how this kind of prediction should be done. It's kind of complicated. The I-JEPA is just doing one single layer, and yeah, the way they encode the latent space also is not like kind of fixed. So that part also took quite a long time for I-JEPA to train. So these are just some of the ways that I think could be improved. Yeah, I think that's more or less it for today. Yeah, I'll just pause here for a while. You have anything you want to discuss about this? Because this is more or less like my view of how we can encode like an intelligence predicting module here. Okay, if not, actually, I think it's quite late already. I think we have more or less covered like all this just now earlier, but maybe we just talk about like, I just give you some like maybe a few seconds on each question. Like I think vision transformers are not a good way to learn, like in terms of like learning the spatial geometries and everything. We could perhaps use like a way to convert the image into various regions, but the regions can be dynamic, like broad to specific, and then we can use attention across these regions. I think similar to vision transformers in some sense, but have dynamic patches, not just a fixed patch all the way. All right. Is prediction in latent space good? Yes. Okay. And we need not just one latent space, we actually should have many latent spaces if possible. And then we can do attentions across the multiple layers of abstractions of this latent space. Is there a way to do self-supervised learning for images? I think the way that is done with the masking is kind of good, right? But perhaps we can learn the encoder first before the self-supervised. Yeah. So how can we incorporate hierarchy into I-JEPA? This was discussed like earlier. We could have more layers, like the prediction of this self-supervised learning need not just be done at one layer. It can also be done at multiple layers. I mean, you can mask out different parts of the image, but you can still do the hierarchical prediction at multiple layers. Okay. Memory used for prediction, yes, it can use to condition the ZAC part of the I-JEPA. So yeah, I think that's more or less what I wanted to talk about today. I think it was quite insightful, the stuff we talked about. Maybe last 5 minutes, anything you want to ask or anything you want to just discuss about? Okay, if not, yeah, thanks for coming. I really learned quite a bit today, like especially the discussion with Richard just now. the layers of abstraction. I think that's going to be the way ahead. Yeah. So I-JEPA provided a good starting framework, okay, with some like loopholes, like I think the context can be learned better, and this prediction can be done at multiple layers as well. Like what was mentioned earlier, you have another abstraction layer down here, another abstraction layer. Let's call it another latent layer, abstraction layer. You can also predict at the next level of latent layer. Yeah, in fact, you can even do this mask token prediction and predict the latent layer with a mask objective. It could even be the same mask as the original layer. Okay, I have to think more about this, but you could do this prediction at multiple layers. And I think this will be a way to make it more of a hierarchy for I-JEPA. Okay, now I'll end here for today. Thanks for coming, and yeah, see you around.